So the focus of today is on the Stampacchia theorem and also the Lax-Milgram theorem. Before to get into that, let's just have some reviews because it will be useful to have that in mind. So as a reminder, we are working here on Hilbert spaces, and up to now we are dealing with real Hilbert spaces. So after definitions, an important theorem that we saw is this projection theorem, right? So you can see that you have here a closed convex subset of H, and you have this geometric, this is a really well-interpreted geometric theorem. Okay. So it's good to have this in mind when we are going to do the Stampacchia theorem. Okay, this projection theorem. Also, so we have this proposition that says that the distance between the projections is less than the distance of the initial points. And yeah, if instead of having a closed convex subspace, I have a linear closed subspace, then I have this characterization of the projection instead. All right, and after that, so in the last lecture, we proved the Riesz representation theorem. So we will also make use of this theorem. Okay, so now let's move to the main point of today, which is the Stampacchia theorem. So all right, we will need also this theorem, the fixed point. So you should know that when XD is a complete metric space, if S is a contraction, so a mapping from X into X such that this inequality holds with some K less than 1, then you have a unique fixed point. So here there's a typo. It's you either put the star here or you remove the star here, but okay, this is a fixed point. Okay, so when you have a contraction mapping on a complete metric space, you have a unique fixed point. Okay, so we'll need that also for the Stampacchia theorem. So we are going to prove that as a review. However, before doing that, let us have a look at the Stampacchia theorem. So for the Stampacchia theorem, we need to define what is a bilinear form and continuous and coercive. So continuity is here. So you have this inequality for some constancy, and the coercivity is given here. Okay, so once you have defined that, the theorem of Stampacchia reads like that. So please pay attention to the fact that, so we work again in this chapter, we work on a Hilbert space, and K is a closed convex subset of H, okay, as in the projection theorem. And you have also as a conclusion, a characterization by some U which satisfies some inequality. Okay, so there's a strong analogy, I would say, between the projection theorem and the Stampacchia theorem. And so after it reads like that. So you have V minus U, and for all V in K, and here you have phi of V minus U. So for any phi in the dual of H, you have the existence of unique U that satisfies this. All right. Okay, so we are going to prove that. And yeah, let's do the blackboard. So we are going first to prove the contraction fixed point theorem, and then the Stampacchia theorem. So let's first deal with the fixed point theorem for contractions. So I recall here the assumptions. So your work X is a complete metric space. So and which satisfies you have some application, some map S such and is such that the distance between S of X and S of Y is less than K times the distance and X and Y with some K less than 1. Okay, those are the assumptions. Okay, then there exists a unique X star X such that S X star equals X star. This is a classical result, so usually you see that on a topology course, but let's do the proof again as a review. So let's do the existence. So the existence, let's start with X node in X, and let's consider the sequence Xn defined by Xn plus 1 equals S of Xn. Under the assumptions, we are going to prove that, in fact, Xn is a Cauchy sequence, and therefore, since X is complete, it converges to a point X or X star, and in fact, X star is a fixed point. So why Xn is a Cauchy sequence? Well, let's look at the distance between Xn and xn plus p for any n and p positive. So if I look at that, I use the subadditivity of the distance, and I get that. So I need to go from xn to till xn plus p. So I will just put this sum from k equals 0 to, let's see. So I will do x on n plus k, n plus k plus 1. And so here I'm going until p minus 1. Okay. This is the triangle inequality or subadditivity of the distance. Okay, I have done nothing here. I just used the property of the distance. Next, we are going to use the fact that since, you know, for example, if I look at, we use the fact that xn plus k, xn plus k plus 1 is less than k, xn plus k minus 1, xn plus k. So applying that, I can go back till the distance between x node and x1. So for example, you have that, let it be more simple than that. You have that the distance between x1 and x2 is less than k x0, x1, because x2 is s of x1 and x1 is s of x node. And if you do d x2, x3 is less than k d x1, x2, and which is less than k square g x node x1. So you can see to go from 0 to 2, you will have, you see here, k2. So I just applied that. So here I start at xn. So I can obtain an estimate by here for k. For k is not good because k is my contraction coefficient. So I will place it by I. All right, for I equals 0, I will obtain here. So k n d x0, x1. And here the sum from a equals 0 to p minus 1 of k to the power I. Okay, this comes just from this remark here on the right. Is that okay? All right, and so this is good because now this is less than k and g x0, x1, and this is less than the sum until infinity, which is 1 divided by 1 minus k. So since k is less than 1, this goes to 0 as n goes to infinity. So I can make that as small as I want as soon as n is large enough. So this means that xn is a Cauchy sequence. So now, so xn is therefore a Cauchy sequence so it converges because x is complete to some, let's say, x star in x. Okay. Now we have that the distance between xn plus 1 and xn, this I know that this goes to 0. We proved that as n goes to n, as n goes to infinity, but this is also the distance between s of xn and xn. And by continuity, so s is continuous because it's a contraction. So, and g also, so this converges to g of sx and x, so x star. So finally, you have the distance between sx star and x star is 0. So this implies that s of x star plus x star. So x star is therefore a fixed point. So the uniqueness finally comes from the fact that if you have two fixed points, so s of x is star plus xi, then you will get that the distance between x1 and x2 is less than the k times the distance between x1 and x2, because sx1 sx2 equals, and so this is not possible unless g equals 0. So which implies x1 equals x2. All right, so we're now good with our fixed point. So we are now going to prove the Stampacchia theorem. All right, so Stampacchia theorem is here. So we will work with a bilinear function, and here a function of the dual. So proof of theorem. Okay, so let's go. So to begin with, we are going to use the Riesz representation theorem. So first of all, phi belongs to H prime. So from the Riesz representation theorem, there exists, and it's unique. Let's call it Z. Such that phi of, let's see, phi of V equals ZV, so sorry, ZV, so Z here. So here it's the product scalar in H, right? So for all V in H. Also, if you fix U, then A U is a linear function. So this belongs to H prime 2. Okay, so you can define a map A such that, so I apply the Riesz representation theorem to A for each U, so such that A U V equals A U applied to V for all V in H. So thanks to the Riesz representation theorem. Okay, now what's the conclusion of the Stampacchia theorem? It says that for all V in K, you have A U V minus U equals phi of V minus U. So, but our A, so the map is linear and continuous. You can prove that. So maybe we'll come back to that. But that's why I could use the Riesz representation theorem. Now, so this, now with what I done, I can rewrite this thing as AU minus V. I will write it as AU and V minus U. And this is nothing but Z V minus U. Okay, so this is equivalent, right? So the conclusion of the Stampacchia theorem is equivalent to that. And sorry, this is not equal. It's not equal. This is greater than. It's greater than. Okay, so next step, I will move my AU here. So I will say, or I can also multiply here by a constant, and we will see after y. So this is also equivalent to, I just multiply here right? Fix any row, a positive number row, and those two are equivalent, right? I will not change my inequality by multiplying by a row. Why I use this row? Because I will need, so the Stampacchia theorem, to apply the Stampacchia theorem, we will need to apply the fixed contraction theorem. And this row will make things work, okay? All right, now I'm going to, so this is equivalent to, I put this side, so I will put this here, and it will make rho z minus a minus rho a u, a scalar with v minus u negative. So it makes me think about my characterization for the projection theorem. I just need to make appear a minus u. That's what I'm going to do right now. So this is equivalent to rho z minus rho a u plus u minus u scalar v minus u non-positive. Okay, so if u satisfies that, this exactly means that u is a projection on K of this thing here. So this is equivalent to rho z minus rho a u plus u, and I will take the projection on K of that equals u. So the conclusion here, so this is what I want to prove. I can rewrite it like that, and this is equivalent to that. All right, so this is equivalent to say that, let's call this S of u, that S of u equals u. So u is a fixed point of this application. So where S goes from H to K, in fact, let's put, and at V, it maps rho Z minus rho AV plus V. Okay, so now if I have a fixed point of this application, I'm done. So now I need to prove that there exists some rho such that this application S is a contraction. Okay, so let's look at SV2 minus S V1. So this is equal to, so this will cancel because this doesn't depend on V. So rho Z minus rho Z, and then I will get minus rho A V2 minus V1 plus V2 minus V1. I forgot the pk. Because S, there's a pk here. I forgot the pk. pk. Okay, but I have this result that the distance between the projections is less than the distance of the points. So if I do that, I'm good. Right, because this is pk of minus pk of, and then I can obtain that. All right, so that means that if I take the square, this will be less than. So now I develop, because this norm is associated with the products, the scalar product. So I will get V2 minus V1 square from here plus, so minus 2 rho A V2 minus V1 V2 minus V1 and plus rho square A V2 minus V1 square. All right, and then I have just this room for one line. I can put V2 my V1 square in front. Yeah, so from the coercivity, this is greater than alpha times V2 minus V1 square in norm. So since I have a minus 2 here, I will obtain the inequality in the other direction. So this is 1 minus 2 rho alpha. And here I use the fact that you can prove that, again, this comes from the property of my bilinear form A. You can prove that you have this inequality. Okay, for all u in H, you have this inequality. You can do that as an exercise. So finally, I will get here plus C rho square. Okay, so finally let's write it again. Finally, you obtain S V2 minus S V1 square is less than V2 minus V1 square times 1 minus 2 rho alpha plus C square whole square. So to apply my contraction theorem, I need just that to be less than 1. I can call it K square, and I would like it to be less than 1. So is it possible to make 1 minus 2 rho alpha plus C square rho square less than 1? This is equivalent to minus 2 rho alpha plus C square rho square less than 0. So alpha, rho is a positive number. So I put it in front. This is equivalent to have rho minus 2 alpha plus c square rho less than 0. So it is sufficient to have minus 2 alpha plus c square rho less than 0. So minus 2 alpha plus c square rho less than 0, which is equivalent to rho less than 2 alpha divided by c square. So I can just choose that. Then I have my fixed point of S. And so the fixed point of S proves that prove the existence of such a U, and this proves the Stumpakia theorem. So this gives the existence of U, and everything we've done comes with uniqueness. There's only a unique fixed point. So uniqueness of U such that so A U V minus U is more than 5 of V minus U. And this proves the theorem. So if you assume that the assumptions of the theorem of Stumpakia are satisfied, and if we assume furthermore that A is symmetric, then the U from the Stumpakia theorem is given by this minimization problem. So the next step is to prove this proposition. So now we are going to prove this this proposition. So, well, so in this case, if A is symmetric, then A defines a scalar product. So, so you can apply. We can apply the Ritz representation theorem to this scalar product. So if we apply the Ritz representation theorem, we obtain that there exists a unique Z in H such that A Z V equals phi of V for all V in H. So So now, the conclusion of Stampakia is that A U V minus U is more than phi of V minus U. So now, if A is symmetric, this phi V minus U is A Z V minus U. So it writes now A U V minus U more than A Z V minus U. So if I put this on the other side, I will obtain A Z minus U V minus U non-positive. But this is exactly saying that U is the projection of Z on K, of course, for the new product scalar. So this is equivalent to say that U equals PK of Z, of course, for the scalar product A. All right, but you know, this is the projection theorem. You know that in this case, U is characterized by, in this case, U is also characterized by what? You minimize the distance. So it says that the distance between Z and U, this is the distance associated to A. So let's write like that. Equals inf of Z minus V A. So let's write it. So this says that A Z minus U Z minus U equals inf, so over V in K of A Z minus V Z minus V. All right, so we need to minimize this thing. So A Z minus V Z minus V equals what? Equals A Z Z minus 2 A Z V plus A V V. But A Z V is phi of V. So this equals A Z Z plus A V V minus 2 A Z V, but A Z V is phi of V. So I need to minimize that, but minimizing that is this is a constant, so which is so what do I say? It is done because now minimizing this expression is equivalent to minimizing This is a constant and can also multiply by a half, and I obtain the result. All right, so to end this this lecture, we are going to state the Lax-Milgram theorem, and this is the Lax-Milgram theorem. So the Lax-Milgram theorem. So the difference is that you don't work with a convex closed subset of H, you work on H. That's the difference between Stampacchia and Lax-Milgram. So in this case, let me some noise here. Okay, so in this case, the conclusion is that there exists a unique U in H such that A of U V equals phi of V for all V in H. We could say that the Lax-Milgram theorem is the Stampacchia theorem when you apply to H. It is as you have the projection theorem. So when you project on K, you have a result with an inequality for the projection theorem. And when you project on the linear subspace, it becomes an equality. And the Lax-Milgram is the same, or there is an analogy. And you transform the inequality of the Stampacchia theorem into an equality for the Lax-Milgram theorem. So the characterization is the same. And the proof is exactly you replace K by H, you apply the theorem. And since H is a linear space, you do exactly the same proof as in the proof of the projection theorem on a linear subspace, and you have your Lax-Milgram theorem. And then the characterization is the same as in the Stampacchia theorem. That's it for the Stampacchia and the Lax-Milgram theorem. Yeah, just to mention, if you want to find a direct proof of Lax-Milgram, you can look into the book of Haller. It's in French, Analyse numérique et optimisation. You can find it.